Thank you for that very kind introduction. And thank you very much for inviting me here to talk today about Robonaut. Something I've been working on for personally more than 18 years, so you can imagine I have quite a history behind there. I'm going to talk a little bit about Robonaut's motivation, where the whole idea came from, our most recent relationship and partnership with General Motors, how the system has evolved over time, the capabilities behind Robonaut, and the fact that we currently have one on the inside of the space station, what process we went to be able to actually launch a Robonaut. And some of the activities we performed on space station and where we're going from here. So our motivation, as Guru mentioned, this is an assistant for astronauts. We hope it to be an assistant in many ways. Actually, we're going after what we call the 3 Ds at NASA, the dull, dangerous, and dirty. If we can send a robot out and assess a dangerous situation before crew goes there, all the better. We don't send cleaning crews up to the space station with the crew, so they have to do a lot of their own housework. If we could help with some of those dull tasks or dirty ones, it would save the crew's time for the more important exploration and science, which is why they're really there on the space station and where they're going for future space missions. Some examples are doing things like setting up work sites and tearing them down. That can take up to an hour and a half out of an 8-hour spacewalk. And our goal is, of course, wherever we send humans, to send assistants to help them. Something that John Kelly said this morning that really resonated with me is that Watson's not here to replace the brain. Well, Robonaut is not here to replace astronauts. It's here to augment and assist astronauts. Robonaut's been around for a while, as I mentioned. We started back in the late 1990s. We actually had 2 original Robonaut 1 robots, and we worked with them in various environments, including working with different lower bodies. It's mostly an upper body system, but we tried it out with different lower bodies to explore its capabilities in different environments. While we were working with Robonaut, actually in the 2006 timeframe, we had put it on a small rover, and we were working with suited test subjects, astronaut-suited test subjects, out in the Arizona desert where they had tested the Apollo lunar rovers. General Motors was doing a worldwide search on upper body dexterity, upper body human dexterity. Their goal, similar to ours, in that while we wanted to help astronauts perform tasks, the General Motors folks were interested in helping their factory workers with very challenging tasks, the things that could be ergonomically challenging or fatiguing, tasks that you can't do once a minute, 60 times an hour, 8 to 10 hours a day. These tasks were actually complicated enough and difficult enough that you had to put people on a restricted amount of time that they can use those. So they did their worldwide search, and they decided that what Robonaut 1 offered was a very good starting point for their investigation into humanoid dexterity to help their factory workers. If you've never seen one before, this is what a secret government lab looks like. General Motors had requested that for competitive reasons they keep the partnership under tighter security, a more closed-lip situation. We set up a team where we brought in 7 government employees, 7 engineers from General Motors, and several of our contractors. We formed a badgeless group, went together, and built Robonaut 2. Here's Robonaut 1 did a great job. Many of the things that it did, Robonaut 2 is actually better. Just to give you an overview of the system, 42 different degrees of freedom for the upper body, 2 7-jointed arms, 12-degree freedom hands, 3 DOF neck, and a 1-degree freedom waist to give it some mobility. Let me have the robot introduce itself here, get an idea for the fluidity of its motions, the different joints actually moving. One of the things that we've always done with Robonauts at NASA is and many of our robots, is we've put soft coverings on them so they can interact with the world in a way that is comfortable for people that come in contact with them. If you haven't noticed yet, the biceps were modeled on mine. So a little bit about our capabilities. The hand obviously is very important if you're going to perform the kind of work to help people in space and on the ground. One of the improvements we made between Robonaut 1 and Robonaut 2 is we added an extra joint in the thumb to give it 4 degrees of freedom. The hand is broken up into 2 sets, the dexterous fingers, which is the thumb, index, and middle, and then the grasping fingers, the ring and the pinky, to help you with power grasps and tool grasps. Metal doesn't grab other metal really well. We put high friction surfaces on our contact elements, on the fingers and the glove, so that when you grab onto something, you have good gripping force. Nothing's going to slide out. We designed the hand for fine motion to position ourselves for performing various tasks. We monitor the tension inside the tendons that actually open and close the hand, so we maintain an appropriate force for the task that we're doing. We actually can perform a wide range of grasps. Here you see what are known as the Kukowski grasp. So if you look at robotic hand literature back in the 80s, this was a definition that was used for machinists and different kind of grasps they perform when they're doing standard machine work. We use this as a starting point for the kind of grasp that we wanted the robot hand to perform, both for our space work and for our collaborative work with General Motors. Here's an example of the dexterity of the hand. Here, turning a knob with the dexterous set of fingers, the index ring and pinky. You can see the white strip there as it rotates. So you don't have to use your whole hand to be able to perform the task. I'm sorry, you don't have to use your whole arm. You can just use your hand, the finger motion from your hand. We made an advancement in our the way in which we control the manipulators on Robonaut 2 versus Robonaut 1. Instead of using traditional strain gauge technology to measure forces and control the forces while performing tasks, we embedded springs into all the large joints on the robot and then measured the position of the spring with position sensors on both sides and used that to not only control the torque and monitor the torque, but control the entire force of the arm and give us the level of force appropriate for the task. And as you might expect, in this case, we distributed a lot more of the electronics versus Robonaut 1 and made it more modular, reduced the amount of wiring running through the system to improve reliability by having fewer connectors. A couple other lessons that we learned going from Robonaut 1 to Robonaut 2 is we made Robonaut 1 so that it could do work in the same fashion in the front of its workspace as in the back of its workspace. It could spin its head around and work right where its backpack is. But we actually never used that. We would always just rotate around. So we got a little smarter and changed the way the workspace was set up. When the shoulders are mounted symmetrically to the body, you get an equal workspace on both sides, as shown in this figure here. This is no shrug. But if you pull the shoulders in, and you can move more of the dexterous workspace to the front of your environment, and then just use that by rotating the robot around as necessary with its weight. Strength is a very important thing for humanoid robots. You'll find lots of cool robots out there in the media. Many of them play instruments, some of them walk carrying trays, a whole variety of really very cool devices. But the focus that NASA and General Motors had was more on performing work. And in this case, oops, a little technical difficulty there. You may have to live with the smaller size of this picture. Oh, that's good. So, on the space station, it actually takes as much as 20 pounds of force to remove and reinstall different maintenance items. And this is what the astronauts are required to be able to perform. 20 pounds is actually pretty significant, especially if it's something you have to generate in any direction. Here we have Robonaut working with a 20-pound weight. And this is a theme that NASA and General Motors shared, to have the payload capability, the strength capability to be able to perform real work, which is something you don't see in a lot of humanoid robots. As a matter of fact, when we bring people into our lab for demonstrations, we normally let them compete with the robot. And they do fine at the beginning, but when the robot comes out to do this, most people aren't doing too well. We actually don't give the robot as much strength as we could. We give it a lot of endurance at the strength that we need, which in this case is that 20 pounds. Human interaction. Of course, if we're going to have a robot working close to a factory worker, or we're going to have a robot working close to an astronaut. Human interaction is critical. R2 is actually smaller than R1, comparable to human. And as I mentioned before, putting on the nice padded skin makes it a very comfortable interaction when you're near it. We wouldn't have it interacting with the Speaker of the House at the time if it wasn't a comfortable robot to work around. From a safety standpoint, that of course is critical. We have multi-level sensors and force limiting so that the robot never exerts a force that's unacceptable. An example of that here. In this case, we have the robot performing a free space task at a reasonably fast motion, something that if you were to walk into the workspace, you might be concerned. But we've designed the robot so it only has enough, we've designed it so that when performing a specific task, it only has enough force to perform its task. So here you're going to see, as I just come and enter the workspace, I can easily restrain it. And then also, it's very predictable. Until that arm is allowed to move on, the robot doesn't continue. That kind of predictability is also a very comfortable thing. We can control Robonaut in multiple different ways. One is through an interface where we build up blocks of different tasks and string them together, different subtasks, then string them together as based on the task that we're trying to perform. Actually, a pretty relatively easy system to work with. Even a semi-experienced operator can perform a task. Another way, which we have found very useful, is through teleoperation. This is where you put on virtual reality gear, and it becomes robot reality gear. You immerse yourself in the robot's environment, and it becomes you. So as you move your hands, move your arms, you can perform tasks, and we can, before we go to automate, we can have a good feel for what a task is going to be like, because we can put a human in the loop and very quickly do a few trials. So I've given you a quick overview of some of the capabilities of the robot, but what can it really do? A very important regime that we were interested in was working with flexible materials. Here we have a space blanket that the robot moves out of the way to acquire another flexible object. Matter of fact, on space station, the crew have to remove certain blankets so the larger robots on the outside of space station can actually come in and interact with specific robotic interfaces. Our theme, of course, is robots helping humans, but we're good with robots helping other robots. Here's an example where the robot's going to interact with its human colleague, and it knows from nonverbal communication that the colleague wants, in this case, the envelope, just by seeing person put their hand over the envelope. The kind of nonverbal communication you and I take for granted all the time, that we want to put into a robot. As I mentioned earlier, Robonaut is on the inside of space station. We were given the opportunity to fly Robonaut with about 6 months' notice. Didn't have time to convert it from a laboratory system to what we call an extravehicular system, or an outside the space station system. But we're taking advantage of the fact that we're working inside the station to learn a whole lot that you can't learn on the ground. Just working in the vehicle, dealing with the microgravity environment, the radiation, all these different things. It's a good place for us to do our demonstrations and earn our stripes and generate a whole lot of interest in what can a humanoid robot do beyond what we originally had foreseen. As part of the preparation for station, safety, of course, was paramount. We have triply redundant systems so that if 2 of them were to ever fail, the robot would never exert an excessive force or an excessive change in force. We check at all sorts of different levels. So before we were able to actually put the robot on station, we proved this out to our safety community in detail. Let me skip past this one. In preparation for station, we sent up our own hardware because when you're a demonstration robot on your first mission, you don't get to work with the same switches and knobs that the crew work with. So we sent up our own system. You can just get an example of some of the basic kind of activities we want to prove out on the space station. So with all that behind us, we were able to launch the system in 2011. can't invite a NASA guy to a talk without a rocket coming with him.
Go for main engine. Go for main engine start. We have main engine start. 2, 1. Booster ignition and the final liftoff of Discovery.
That was one Robonaut waving goodbye to the other. Okay, if you weren't awake before, you are now. And I put this one in there more for anecdotal reasons. The space station crew unpacked our robot on station and told us there was no robot there. They actually had done is they had unpacked it.
That's what we're afraid of.
Repacked all the packing material and then told us, and they hid it inside the space station. After it was pretty humorous after we see. One of the first things we did, like working with any kind of programming system, we had the robot say, "Hello, world." And by the way, I found out you need pinkies to say "Hello, world" in American Sign Language. One of the next things was our first human interaction in space. Here, the robot is designed to feel the force of a person trying to initiate a handshake and then complete the handshake. That's Colonel Dan Burbank, who was the commander of Space Station at that time. Actually, Saturday Night Live picked up on this and made some comment about how the robot had completed its initial checkout and now was going to its Plan B operations, which with all this ominous wording behind Plan B. That same power panel you saw on the ground, here we're operating with it on Space Station. And we found that the robot behaved reasonably similar on the ground as we expect, as it has on orbit. Now, the environment doesn't behave quite as the same. So when you work with switches like this, covers are there for a reason, of course. You have to make sure you cover that before you go on to the next part of your task. So this was our initial work towards working with different equipment, starting with switches and buttons. Then moving on to tool use. This is an airflow meter that the astronauts use to measure the airflow coming out of the various vents, and they feed the information to the people in mission control to make sure the vents are working properly. Using the robot and being able to look through its eyes, the people on the ground for the first time could read the meter themselves as opposed to getting the average number from the crew person. And if your whole job is making sure the airflow is really performed properly on Space Station, seeing the raw data is really exciting. And the robot would just move this meter, this airflow measuring stick from one location to another. I mentioned earlier soft goods. Try that again. So here, the two different views are switching back and forth between the robot's view and the camera that the crew set up for us. Here we are getting a wipe, and actually the crew have to clean down the handrails every Saturday or every other Saturday. And they use baby wipes that have been certified for space, which I don't think requires a whole lot to certify your baby wipe for space. Now you can see working with various grasps to first acquire the wipe from its holder, and then the robot will hand it off to its other hand to position it better for actual cleaning. I'm going to skip ahead directly to the cleaning for time. Now, they're really excited about this because they don't have to do the cleaning, all the better. So they were taking a lot of pictures of the robot actually cleaning across the handrail over here. Now, I mentioned the teleop before. Here was our first teleoperation in space. You can see astronaut Tom Marshburn in the background. He's wearing similar virtual reality gear. And his crew colleague was making it a little difficult for him spinning that duct tape very rapidly. My guys, this is my first try at doing this. So he slowed it down a bit, and we had our first capture. Of course, of all things we capture in our first time in space is a roll of duct tape. But everybody was happy with that. So what did we learn? What did we learn initially on station? Safety, of course, is critical. We actually made the robot more sensitive than it needed to be. If the crew bumped into it, it would turn itself off. Things are kind of limited when you're working in space. You have to keep your speed down, so you keep your momentum down. You can't exert a lot of energy. And also, safety and control must be clearly separated, because we were in a pretty much of a rush with that 5 or 6 months to get ready for station. We didn't divide our software as well as we wanted to. We have since gone back and done that, so that as long as you're not making any change to the safety system, then you can put on all these different layers of controls above that without worrying about exerting excessive force or having an incident. Communicating with the space station is a challenging thing. There are loss of signals constantly throughout the orbit for various points in time, so you can't have people on the ground doing things that could cause the robot to do something hazardous. All that must be protected against inside the robot. All the safety systems are local to the robot. And having it up there, we've built some trust. It's got a lot of predictability. It's a cool robot. Matter of fact, the crew once called me from space station asking to work on the robot in their free time because they wanted to just experiment with it. But they asked to do it on Christmas Eve, and I didn't have the heart to ask my team to stay Christmas Eve to do that. So where are we going from here? Being able to maneuver inside the space station is a really good first step, using the space station as a laboratory for us to learn how to climb on the outside of the station. As we're learning on the inside, if we have issues, the crew is always there to help us. Once you go outside, it's a lot more difficult to get assistance. So we want to gain experience before we have a robot on the outside in what the forces are like and what the steps are like, what is the actual concept of operations as we're going through the space station. And along the way, if we can do some more of those, if we can do a few of the cleaning tasks and help the crew out to pay them back, all the better. So subsequently, we have now launched legs onto space station, and they've been assembled with the robot. And you'll see before I used my whole hand to stop the robot, one finger. We have learned a few things in several years. And instead of the robot shutting itself off, we have it just pause. We also really improved our control scheme, so we can vary the stiffness of any limb over a great range. So as you're moving through the station, nice soft limb is not going to cause any issues. And then you make it nice and stiff when you have to use it as an anchor during a task. Here at the space station, right at Johnson Space Center, we have a simulator for offloading the weight of a system. In this case, there's Robonaut with its full set of legs. And here we're practicing climbing on the ground as a precursor to doing it in space. Unfortunately, you can't reproduce zero-G as well as you would like on the ground. Here, if the robot bends forward, you generate moments that wouldn't exist on the station. So you have to learn to actually work in this particular environment. We started to add more automation. What happened right there was a camera system inside the actual foot of the robot, looked on the handrail, found a place where there's nothing in the way, grabbed onto it, and then the force control removed all the forces before clamping onto it. So this is a little sped up, but the idea is to be able to work inside the station, moving across handrails and moving things around, getting things set up, helping with inventory, things of that nature. With the ultimate goal being on the outside of space station to perform with those really high payoff tasks like saving an hour, hour and a half of crew time on the outside of the space station. Now, simultaneously on the ground, we've been using our teleoperation setup to see how far of a range of tasks the robot can perform. We actually had a few oil and gas folks in town, and they were very impressed that we could pull the sheath off of this hose without pulling it out of the other hand of the robot. It's using a combination of our force control and the proper level of proper grasp to keep that grip in place. And if you look very carefully in the teleoperator's insert view over there, you'll see a little black line that indicates the damage area that simulates a real piece of damage that could be on an actual hose. I don't know if you've read in the media, but a year or two back, we were having quite a few ammonia leaks on space station. If we could find leaks like this, either through this inspection technique or through this next one, that would be a great boon. Here, we're using a flashlight to simulate an ammonia detector that you would run against different parts of the space station looking for an ammonia leak. And even a little more into our dexterity level here. Here's working with what we call tether hooks. Crew have to tether and untether objects all the time as they're moving around on the outside of the station. Grabbing a device like this is not easy. Teleoperator, of course, is able to do it reasonably well, taking advantage of the dexterity of the system. Automating that is far more of a challenge. We've also been working with, no, it's not behaving quite well, hang on. Oh, that's better. So we work with the Methodist Hospital, which is part of the Houston Medical Center, and one of the doctors there performs the ultrasounds for the astronauts when they come back from their missions, and he wanted to see how well Robonaut could perform an ultrasound with the thought, thinking that significantly down the line, perhaps the robot on station could assist during an ultrasound. So here we have grabbing an ultrasound device and a needle for injection, which is frequently part of an ultrasound procedure. Our teleoperator looked through the robot's eyes at the actual ultrasound display and was able to adjust the force to provide the right level of force contact during the procedure so you could have a clear view of what was underneath the skin on the neck. As a matter of fact, Dr. Garavi made a comment that he had an easier time teaching our teleoperator and the robot versus his own medical students in terms of performing an ultrasound, but we made a deal not to tell the medical students. So actually, I'm done pretty much in time. I have a few seconds to talk a little bit about a spin-off here that I wanted to mention. This is called a RoboGlove. This takes the same technology in the Robonaut hand and puts it into a glove that weighs about 1 pound 7 ounces, so a person can reduce their strain during grasping. This is one of the big things that General Motors has gotten out of this. I mentioned at the beginning they were interested not so much in the humanoid robot, but in the technology behind it. This is one of our first spin-offs that they have tested at their facility, at one of their assembly line prototype facilities, showing that you can get a significant reduction in strain when you're performing tasks with this glove on, because it relieves the load on the human tendons and picks it up with robotic tendons. And we're also at JSC looking at the same technology to put into spacesuit gloves, because astronauts have to fight a pressure differential between the inside of the spacesuit and the zero pressure outside, which is very fatiguing over time. And with that, I will stop.